Really glad to get to join you folks, and my apologies for my part of the fail. My laptop seems to have died between before dinner and now, but we're good to go here. So yeah, I want to talk to you this evening about how general relativity shaped 20th century philosophy of science. And if I might begin with a sort of a pun here, a different kind of gravitational wave, the publication of General Theory of Relativity, late fall, winter of 1915, 1916, produced a significant disturbance in the field of philosophy of science, one whose effects are still being felt to this very day. Philosophy of science after that point was a very different enterprise from what it was before. A little bit more, let me unpack the main thesis in a little bit more detail. I want to argue that much of the fine structure of 20th century philosophy of science is shaped by the set of problems that the philosophers of science of that generation were dealing with, having to do with the general theory of relativity, including the logical structure of the theory, the empirical interpretation of the theory, the ontology of GR, helped shape the way we think about the ontology of physical theory more generally. And while I won't talk about it very much this evening for the sake of time, also the heuristics of scientific discovery. In the main, the way this happened is that those debates of the late teens and early 20s led to a structure on the problem space that mainly pitted Neo-Kantians of one variety or another against what came to be after about 1921, 1922, and I'll walk you through the chronology, what we recognize as the mainstream right-wing Vienna Circle logical empiricist tradition. Another point by way of preamble, and I'll unpack this in a little bit more detail in just a moment. We've got to remember that Einstein in this story is not just the guy who invents the theory of the theory that stimulates all of this philosophical activity in the next and succeeding years. No, Einstein himself was one of the philosophical players in this story. Incredibly sophisticated, even by the higher standards of his time, in philosophy of science, also history of science, was in regular, intimate contact with all the major philosophical players in the story that I'm going to lay out for you as well in a moment. He was really a contributing member of this philosophical discussion. A little bit more specifically now still, and I want you to remember this framing device for the rest of the talk. When I talk about mainstream right-wing logical empiricism, I mean the view that is classically associated with the later Moritz Schlick, with Hans Reichenbach, according to which, and this is the key philosophical principle that drives this version of logical empiricism, according to which the way in which theory contacts the world is via a set of individual coordinating definitions for every primitive concept in the theory. Each of those concepts, via those coordinating definitions, acquires a determinate empirical meaning, concept by concept, from which it follows that individual propositions built up out of those concepts themselves also have determinate empirical content of such a kind that the relevant observations or experimental results decide the truth or falsity of those propositions univocally. That contrasts with, that's what we call the right-wing view. That contrasts with what today in the literature we customarily call the left wing of the Vienna Circle, which is chiefly associated with Otto Neurath, the physicist Philipp Frank, the mathematician Hans Hahn, by contrast with the right-wing view, followed a kind of Duhemian, holist, underdeterminationist way of thinking about the manner in which theory meets world. In other words, the key idea being that it is not individual concepts and propositions that one by one acquire empirical content and then are testable one by one, but only whole bodies of theory possess empirical content. And as you will see, that left-wing view also turns out to be Einstein's view. In telling this story, I want to follow roughly two narrative lines, two threads through the argument space. And the first of these that we'll look at is the discussion that was engendered in late 1915 about point coincidences. I'll unpack all of these concepts. What's called Eindeutigkeit, or the univocalness in the way in which a theory does or does not represent reality. And consequent upon this, the ontological commitments and empirical interpretation of general relativity. The second narrative thread is one that will highlight this debate between the logical empiricists, what I hear termed the new empiricism, the right-wing logical empiricists, the Neo-Kantians, and conventionalists of this Duhemian variety, including Einstein. These two lines of discussion both begin in December of 1915. Shortly thereafter, they diverge and wend their own way, and then they reconverge in the early to mid 1920s. Okay, so let's begin by remembering two facts that are crucial to this story. And the first is that, as I mentioned earlier, even by the higher standards of his day, Einstein was uncommonly well trained, uncommonly well read in the best history and philosophy of science of his day. Let me just highlight some of the facts about his training. So if we look to what he was doing while he was a student at the Swiss Federal Polytechnic, 1896 to 1900, when he was skipping out on most of his lectures because he was bored to death by them, he was off reading on his own, not just the best physics of the day, but also the best philosophy of the day, the best history of science of the day. We know for a fact that he read Mach's History of Mechanics and his History of the Principle of the Theory of Heat. The letters have really interesting discussions of his first encounters with Schopenhauer, who became a hugely important figure in Einstein's intellectual formation. We are pretty sure that he read Lange's History of Materialism, one of the classics of that era, Eugen Düring's Critical History of the Principles of Mechanics, this remarkable book on Newton that should be translated someday into English. I think it's one of the best books ever written on Newton, Ferdinand Rosenberger's book, Isaac Newton and His Physical Principles. Also in the classroom, and he did attend these lectures because he really enjoyed them, in the summer semester of 1897, he took the lecture course by August Stadler on the philosophy of Kant. Stadler was one of the leading Marburg Neo-Kantians of the day, especially well known for his work on Kant's philosophy of matter. And then he took, in the winter semester of 1897, Stadler's course, Theory of Scientific Thought, Theorie des wissenschaftlichen Denkens, which is just a straightforward philosophy of science course. And as an aside, one notes when you read the transcript that that course was identified as a so-called obligatorisches Fach, meaning a required subject. Every physics student at the Polytechnic in those years had to take Stadler's philosophy of science course. But his self-education continued after he left the Polytechnic, when he went off to Bern to start his job at the Swiss Federal Patent Office. He formed this informal, once-a-week evening discussion group, grandiloquently named the Olympia Academy. And you see his friends Habicht and Solovine, who joined him in this. We have the whole reading list of the Academy. Among the things they read during a period of about 2 years, Avenarius's Critique of Pure Experience, Dedekind's What Are and What Should Be the Numbers, Hume's Treatise, Mach's Analysis of Sensations, Mill's System of Logic, Pearson's Grammar of Science, Poincaré's Science and Hypothesis, and so on and so forth. So that by the time 1905 rolls around, Einstein has read all of the most important philosophy of science literature that will play a big role in these discussions that grow up after 1915. So just to summarize, he had read all of the major works of Ernst Mach, he had read all of the major works of Henri Poincaré, and he had read Duhem's Aim and Structure of Physical Theory in the German translation that was done at the behest of none other than Ernst Mach. And by the way, there's a really interesting story there about Mach's role in promoting Duhem's philosophical project in the early part of the 20th century. The second fact that I want us to remember before we plunge into the narrative is that many of the philosophers who are part of this discussion, in fact, virtually every philosopher who is part of this discussion, was in the early part of the 20th century, even before 1915, but continuing after, intensely engaged in physics. And let's just look at a few of these individuals to get a feel for how serious was their engagement with physics. So we start with Moritz Schlick, remembered as the leader of the Vienna Circle after 1922. His PhD was actually in physics, taken under the direction of Max Planck in Berlin in 1904. He retrained himself in philosophy and philosophy of science more specifically, with independent study at the University of Zurich. After he got his first job at the University of Rostock in 1911, he began a very intensive engagement with the philosophical implications of the theory of relativity, starting with, of course, special relativity, but then moving on to GR. I'll talk in some detail about his remarkable 1915 paper on the philosophical significance of the relativity principle, and also in some detail in a few moments about his splendid 1917 monograph, Space and Time in Contemporary Physics. So intense engagement with physics. Hans Reichenbach is also going to be an important part of this story. He did his PhD at Erlangen in 1915 with a dissertation on theory of probability that evolved into his early 30s book on probability. But in the late teens, he was in Berlin, and he was auditing Einstein's GR lectures from that time. We have his notes from those lectures. They're a fascinating read. He then went on to become a Privatdozent at the Technical Hochschule in Stuttgart, and published, well, previous to that, when he was still in Berlin, he published his first book, Relativity Theory and A Priori Knowledge, about which we will talk in a bit. Followed in 1924 with his book on the axiomatics of the relativistic theory of space-time. And then, of course, his very well-known book, his 1928 book, Philosophy of Space-Time Theory. Just a little aside to show you how physics and philosophy were interrelated at this time. He was appointed an extraordinary professor in Berlin in 1926. But even though he was trained as a philosopher, his appointment was in the physics department. Why? Partly because he was a well-known student radical from the late stages of the First World War. He had been a leader of the student socialist movement at the University of Berlin, and the conservative philosophy faculty would have nothing to do with him when Einstein wanted to bring him to Berlin. So Einstein and Planck engineered the creation of a new chair in the philosophy of science in the physics department at the University of Berlin, and Reichenbach was appointed to that. And then, of course, Carnap, whose PhD dissertation under the Neo-Kantian Bruno Bauch at Jena in 1921 was on space. And it's a very sophisticated philosophical discussion specifically about how GR has transformed our understanding of space. For the next 6 years, virtually until he did his habilitation in Vienna, virtually everything he wrote had to do with philosophy of physics in one way or another, including this little known but really lovely monograph from 1926 called The Construction of Physical Concepts, Physikalische Begriffsbildung. So yet again, intense engagement with the best physics of the day. Well, let's turn to the story, and let's next remind ourselves of some important points about the genesis of the general theory of relativity, starting with the fact that I hope is known to a lot of people in the room, which is that 3 years before introducing the correct version of GR in 1915, Einstein had published a preliminary version of the theory. Today we call it the Entwurf theory, from the German word for outline, because that was the first word in the title of the first paper that he and his colleague Grossmann published on this topic. And he published repeatedly on this version of GR between 1912 and 1915. And what's noteworthy about the Entwurf version of the theory is that it is not a fully generally covariant theory. Okay? There were a number of reasons why Einstein at that time thought that the correct theory of gravitation could not be fully generally covariant. One problem he had is that he misunderstood what kind of Newtonian limit he should be taking. But of more philosophical interest is what's known as the whole argument. And we don't have time for me to walk you through all the details here, but very, very briefly. The idea here is that he had wrongly convinced himself that a fully generally covariant theory of gravitation would be inadequate in this very interesting respect, namely that in regions of space-time devoid of matter and energy, so-called holes in space-time, that in such regions of space-time, a fully generally covariant theory would not fix a unique solution to its field equations for those holes in space-time. And Einstein thought that that was a fatal problem with a fully generally covariant theory. Hence the Entwurf theory with its restricted covariance properties. But then, of course, starting in November of 1915, Einstein publishes the correct version of GR, the fully generally covariant version of GR, summing it all up in this masterful early 1916 review paper in the Annalen der Physik, the foundations of the general theory of relativity. Many people, well, one other thing before I make that remark. Just as Einstein is publishing those 3 papers in November of 1913, just after he publishes those, there lands in his inbox this essay by Schlick that I mentioned before on the philosophical significance of the relativity principle that is a remarkable piece of philosophy of science. We don't have time for me to share with you all the really cool stuff that's in this paper. But one thing that's very important that I do want to talk about briefly right now, because it's part of the background to what is to come. In this paper, he reiterates a view that he had first introduced in 1910 in a paper on the essence of truth according to modern logic, where he introduced this conception of truth, and sort of a weird conception of scientific truth, as a one-way univocal correlation or coordination between theory and world, or theory and fact. One way in which direction? One way in the direction from theory to world, but not in the other direction. In the direction from world to theory, Schlick argued, and we don't have time to go through the details, but take home point. Schlick argued that it is an inevitable consequence of this way of thinking about truth that there will always be a multiplicity of different theories that are equally univocally coordinated with a given body of fact, equally univocally coordinated with the world. What Schlick is doing here is developing a version of something very close to Duhem-like underdeterminationist conventionalism, but from a very different set of premises than Duhem worked from. How Schlick's own views change is one of the things I'm going to want to talk about as we go along. Einstein was astonished when he read this paper, and he wrote back to Schlick, letter of December 13 December, yesterday I received your essay and I've already studied it through completely. It is among the best that have until now been written about relativity. From the philosophical side, nothing at all appears to have been written on the subject that is nearly so clear. At the same time, you really have complete command of the subject. There is nothing in your exposition with which I find fault. Uncommonly high praise from Einstein. What happens after that exchange of letters is that Einstein and Schlick become not just professional colleagues, they become good personal friends. Schlick visits Einstein in Berlin a lot. Einstein takes the train up to Rostock on a number of occasions. There's a huge correspondence between them over the next 5 or 6 years. This was one of the most significant intellectual relationships that Einstein had at this time. So now let's start the first narrative. Point coincidences, univocalness, Eindeutigkeit, and ontological commitments and empirical interpretation of GR. When Einstein published the correct version of the theory in November 1915, more than one of his correspondents noticed that that argument, the whole argument that had previously been put forward as a killer argument against a fully generally covariant theory, that this wasn't even mentioned. Well, there's a glancing mention in the second of the 3 papers, but really wasn't discussed at all. And they wrote to him and they said, literally, said, what happened to the whole argument? We thought this was this devastating objection to the theory. And Einstein wrote back to a number of his correspondents. And I'm going to share with you a couple of these letters, starting with this letter to Ehrenfest from 26 December 1915. We can skip over the first paragraph, which just says everything in that last paper from early 15, late 14. He says everything was right, except when I got to the point about the whole argument. And then he says this, in place of section 12, paragraph 12, the following reflections must appear. The physically real in the world of events, in contrast to that which is dependent upon the choice of a reference system, consists in spatio-temporal coincidences, footnote, and in nothing else. Real are, for example, the intersections of 2 different world lines, or the statement that they do not intersect. Those statements which refer to the physically real, therefore, do not founder on any univocal coordinate transformation. If two systems of the G mu nu, or in general the variables employed in the description of the world, are so created that one can obtain the second from the first through mere space-time transformation, then they are completely equivalent, for they have all spatio-temporal point coincidences in common. That is, everything that is observable. That point about how now the space-time coordinatization itself doesn't, well, in fact, let me step back and let me summarize or paraphrase in a slightly different way. What Einstein is in effect saying here is that his mistake in the whole argument was wrongly thinking that simply applying a coordinate chart in space-time sufficed to individuate manifold points. Again, we don't have time to track why that's the crucial premise in the argument. But what he's now convinced himself of is that a mere coordinate chart has itself no physical significance whatsoever and can't be sufficient for individuating manifold points. And that instead you have to individuate manifold points in some thoroughly covariant manner, as with individuating them as points of intersection of world lines, or, to use the word that becomes very common in the discussion over the next several years, point coincidences. He glossed that insight many times in these months and years by saying, as he said in a letter to Schlick on 14 December 15, time and space thereby lose the last vestige of physical reality, which again means space and time, meaning a coordinate chart, doesn't suffice to fix the point manifold ontology of the theory. Or here he is writing to Michele Besso, one of his very closest personal friends, in early January 1916. In the Lofbetrachtung, the whole argument, everything was correct up to the final conclusion. There is no physical content in the existence of 2 different solutions, g of x and g prime of x, with reference to the same coordinate system, K. Attributing 2 different solutions to the same manifold is senseless, and the system K has indeed no physical reality. The following consideration takes the place of the whole argument. From a physical point of view, nothing is real accept the totality of spatiotemporal point coincidences. If, for example, physical processes, das physikalische Geschehen, and by the way, remember that phrase, I want to come back to that in just a moment. If physical processes were to be built up solely out of the movements of material points, then the meetings of the points, i.e. the points of intersection or coincidence of their world lines, would be the only reality, i.e. observable in principle. These points of intersection are naturally preserved under all transformations and no new ones are added if only certain uniqueness conditions are maintained. Thus it is most natural to demand of the laws that they do not determine more than the totality of the spatiotemporal coincidences. According to what has been said, this is already achieved by generally covariant equations. One of the things that's interesting, you should be noticing in some of these excerpts from the letters, is the way in which he intertwines ontological and epistemological issues here. What's distinctive about point coincidences is both that they fix the real ontology of the theory and they fix what is the observable content of the theory. Here's yet another letter. I won't read this whole letter, but it's just really a cute one, so I'll just paraphrase it. Ehrenfest is having a lot of trouble getting his head bent around this, and Einstein goes into good teacherly pedagogical mode, being very gentle with him, and there are several letters that go back and forth, and culminates with this letter from Einstein to Ehrenfest, where Einstein comes up with this cute little thought experiment for illustrating the main point of the point coincidence argument, as we now call it. So Ehrenfest had suggested this schema. You've got a star, you've got a screen, and you've got a plate. He asked Einstein the question. He said, when the light from the star hits the screen, wouldn't it be the case that the direction of the wave normal at the screen would always turn out to be the same, regardless of the coordinate transformation you might apply to describe this? And Einstein says, well, indeed it would, and that's just the point that you are missing. And so he says, let me try to explain by having you imagine you do the following thing. So you take that diagram, okay, you trace it on, as he says, deformable tracing paper. Imagine rubbery tracing paper, okay? He said, okay, so you trace that figure, then you screw up that deformable tracing paper, and you're going to get something that looks like that. And then you lay that back on the original drawing, and it looks as if you've got two physically different situations. But the point of the point coincidence argument is that since space-time points are individuated only as points of intersection, such as the point where the photon hits the screen and where the photon hits the plate, and so on and so forth, the physical content of these two representations is exactly the same, so that in fact the fully generally covariant theory, now thanks to the covariance properties of the theory, of necessity will satisfy that requirement of univocalness, or Eindeutigkeit as he calls it, in the representation of the theory. We'll skip this one for the sake of time, just saying much the same thing in the big review paper of 1916. A side question that's not directly relevant to the main narrative here, but it's a very interesting one, is from what source did Einstein learn to think this way about this so-called univocalness or Eindeutigkeit principle as a necessary condition on the acceptability of scientific theory? Well, this is the man that he learned it from, someone who's totally unknown today, a minor positivist of the late 19th, early 20th century, Joseph Petzold, who introduced this idea in an 1895 paper that was extremely widely read and extremely widely cited back in the day, that was just called Das Gesetz der Eindeutigkeit, the law of univocalness. In that paper, Petzold writes, we must bring to bear on nature a certain general presupposition without whose confirmation we ourselves could not live, either mentally or bodily. Such a presupposition lies at the base of all scientific research, something of which we may be more or less consciously aware, and we may be of the firm conviction that it will hold up everywhere, since we could not conceive of ourselves with our particular mental nature if we once imagined it being given up. Both our individual constitution and that postulate, as we may designate the relevant presupposition, belong inseparably together. The latter, the presupposition, consists in nothing other than the assumption of the thoroughgoing complete determination or as we want to say, in order to emphasize the most important side of the matter, in the assumption of the uniqueness of all processes. Eindeutigkeit aller Vorgänge. Remember that expression Einstein had used, Eindeutigkeit des Geschehens? He's echoing Petzold's own language in the way he talks about this. But Petzold himself had applied this idea to thinking about the general theory of relativity in its early Entwurf form. He wrote in this 1912 paper, "The task of physics becomes thereby the univocal, eindeutige general representation of events from different standpoints, moving relative to one another with constant velocities, and the univocal setting into relationship with these relations. Every such representation of whatever totality of events must be uniquely mappable into every other one of those representations of the same events." And notice the footnote, better representations of events in arbitrarily many of those systems of reference that are univocally mappable into one another are representations of the same event. Identity must be defined since it is not given from the outset. That's exactly the insight that lay behind the point coincidence argument and Einstein's diagnosis of his error in the whole argument. And then continuing the quote, "The theory of relativity is one such mapping theory. What is essential is that univocal connection. Physical concepts must be bent to fit for its sake. We have theoretical and technical command only of that which is represented univocally by means of concepts." I'm going to skip the next couple of slides, which are just meant to drive home the point of how close Einstein was to Petzold during these years, and skip on to this. At the same time, there's a discussion growing up in foundations of mathematics, geometry, and formal semantics about this property that in formal semantics we have come now today to call the categoricity of a theory, which is simply the idea that an axiomatic theory is categorical if it fixes the class of its possible models up to the point of isomorphism. And so in that way fixes a structurally univocal, structurally unique representation of that which it aims to describe. This concept is introduced into the Foundations of Geometry literature by Hilbert in his 1899 book on the Foundations of Geometry. It was given a more refined expression by the American mathematician Oswald Veblen in 1904. And by the way, here's a quiz question. So I'm sure nobody knows the answer. Does anybody know where the term categoricity came from? What inspired Veblen to use that term? Right? All of you guys are interested in category theory, you need to know this part of the story too. Right? It was none other than John Dewey. And there's a footnote to Dewey in that 1904 paper. That's another story that's a fascinating one. But again, this discussion of categoricity in formal semantics, foundations of mathematics, set theory, that takes on a life of its own and is interwoven in later years with the Petzoldian discussion of univocalness as a general methodological requirement on all acceptable scientific theories. And those two threads come together especially interestingly in a 1927 paper of Carnap's, to which I will come back later on. This paper called Proper and Improper Concepts, which was published in an obscure journal and has only recently become available in English. I urge you to read it. It's a fascinating paper. And the key idea here is he distinguishes between what he calls proper and improper concepts. Proper concepts are categorical concepts, or as they sometimes said in the German literature that day, monomorphic concepts. And they are such thanks to the fact that they are defined via explicit definitions in terms of the primitives of one's protocol language, be it a phenomenalist or a physicalist protocol language. By contrast, improper concepts are non-categorical concepts that are defined only implicitly by the systematic role they play in the axiom system. And the main point of Carnap's argument in this paper is to argue that it is a necessary condition on the empirical interpretability of scientific theories that you have at the foundation as your empirical primitives only proper concepts that are defined by explicit definitions. In a moment, we're going to start talking about coordinating definitions, to use the term of art that is introduced into this literature a few years earlier. And that what distinguishes those proper concepts, which is their very categoricity, and that it's only thanks to their determinateness of meaning that they can do the work of infusing physical theory with empirical content. One other thread that I want to track for just a few minutes is there's a very interesting discussion that goes on over the course of several years about the distinction between what, in a paper I wrote a number of years ago, I called point coincidences and pointer coincidences. In Schlick's 1917 monograph, Space and Time in Contemporary Physics, which, as he explained to Einstein, he wrote mainly to explicate Einstein's point about how, in a fully generally covariant theory, space and time have lost all of their physical significance, all of their objectivity. In this essay, the notion of point coincidences plays a huge role. This book, too, Einstein thought was just spectacular. He wrote in May of 17, again and again, I look at your little book and am delighted by the splendidly clear expositions, and the last section, Relations to Philosophy, appears to me to be excellent. But here's Schlick talking about the significance of point coincidences. Experiences of coincidences must be taken into consideration here. In order to determine a point in space, one must somehow directly or indirectly point to it. One must make the point, a compass, or a finger, or a set of crosshairs coincide with it. That is, one sets up a spatio-temporal coincidence of two otherwise separated elements. Now, it turns out that these coincidences always appear to agree for all of the intuitional spaces of the various senses and for various individuals. Remember that point. For just that reason, an objective point is defined by them, i.e. one independent of individual experiences and valid for all. Upon more careful reflection, one easily finds that we arrive at the construction of physical space and time exclusively by this method of coincidences and in no other way. The space-time manifold is precisely nothing other than the totality of objective elements defined by this method. Exactly Einstein's point in the point coincidence argument. This is the result of the psychological empirio-critical analysis of the space and time concept, and we see that we encounter precisely the significance of space and time that Einstein recognized as alone essential for physics, and there gave proper expression, for he repudiated the Newtonian conception and instead founded physics on the concept of the coincidence of events. Well, actually, Einstein, for all of his praise of that booklet, did disagree with Schlick on one very interesting issue related to the notion of point coincidences. So he writes in a letter to Schlick, 21 May, writing about the monograph in that last section on philosophical implications. He writes, "The second point to which I want to refer concerns the reality concept. Your view stands opposed to Mach's according to the following schema. Mach says only impressions are real. Schlick says impressions and events of a physical nature, think space-time point events, are real. Now it appears to me that the word real is taken in different senses according to whether impressions or events, that is to say, states of affairs in the physical sense, are spoken of. If two different peoples pursue physics independently of one another, they will create systems that certainly agree as regard the impressions, elements in Mach's sense. The mental constructions that the two devise for connecting these elements can, however, be vastly different. And the two constructions need not agree as regards the events, for these surely belong to the conceptual constructions. Certainly only the elements, but not the events, are real in the sense that they are given unavoidably in experience. But if we designate as real that which we arrange in the space-time schema, as you have done in your theory of knowledge, then without doubt the events above all are real. Now, what we designate as real in physics is no doubt the spatio-temporally arranged, not immediately given. The immediately given can be illusion. The spatio-temporally arranged can be a sterile concept that does not contribute to illuminating the connections between the immediately given. I would like to recommend a clean conceptual distinction here. This seemingly minor disagreement that Einstein expresses here with Schlick will become the sort of the seed of what turns into a much, much stronger descent from Einstein to the direction in which mainstream right-wing logical empiricist philosophy of science is going to start going in just a couple of years after this. Sake of time, we're going to skip that slide for that one too. Let's turn to the second narrative thread now. Neo-Kantianism, conventionalism, and the new empiricism. And let's begin by reminding ourselves of just some conceptual background here. And in particular, I want to have you remind yourselves about the important difference between Poincaré's version of conventionalism and Duhem's version of conventionalism. So think about this in the context of Poincaré's geometric conventionalism. He argues symmetrical geometry only gets empirical content through conventional definitions, as with the definition of straight line segment as segment of the path of a ray of light. And conventional definitions are distinguished for Poincaré from contentful empirical assertions, such as the ascription of a metrical structure to space. The moment of conventionality in Poincaré's version of conventionalism is confined exclusively to those conventional analytic definitions, the assertion of which is what fixes the empirical content of the remaining synthetic empirical propositions. But remember, by contrast, Duhem thought that the element or the moment of convention in science is not confined to the coordinating definitions, these analytic definitions, straight line, path of a ray of light, so on and so forth, but is instead spread over the entire web of belief, to use the Quinean expression. It's a consequence of his holist version of underdeterminationist conventionalism. And I want you to hold that contrast clearly in mind between confining the moment of convention to the coordinating definitions and letting the conventionality spread throughout the entire body of theory. That's an important background to what is to come here. So Schlick, as I mentioned a while ago, this is the same slide you saw before, in that 1915 paper, had already introduced his own sort of quasi-Duhemian version of underdeterminationist conventionalism, derived from his own theory of truth. This became the foundation for his way of thinking about the role of convention through the early 1920s. But now, specifically, in 1917, he wrote this in the Space and Time in Contemporary Physics. Every theory consists of a structure of concepts and judgments, and it is correct or true if the system of judgments is univocally correlated with the world of facts. It is, however, possible to indicate the same set of facts by means of different systems of judgments. Consequently, there can be different theories for which the criterion of truth holds in the same way, and which then do justice in equal measure to the observed facts and lead to the same predictions. They are different systems of symbols that are coordinated to the same objective reality, different modes of expression that reproduce the same set of facts. So again, this sort of quasi-Duhemian, more holist way of thinking about the moment of convention in scientific theory. That's background then to the Neo-Kantian reaction to general relativity that sets in the latter part of the teens. And in particular, immediately after World War I, there is a sudden explosion of literature about general relativity from Neo-Kantians of every stripe. Some of it's really good literature, as with Cassirer's book on Einstein's theory of relativity. Some of it's really crappy literature. The arguments ranged from people simply saying that since general relativity challenges the a priori status of Euclidean geometry, GR has to be false, to people who try to draw a distinction between physical space and psychological space and say Kant was right about psychological space, but perhaps not physical space. And then there was this utterly wacky guy, Hugo Dingler, who gave the following argument, and I joke not when I paraphrase his argument. His argument was that it is logically impossible for forgetting exactly how to formulate the point here. It is logically impossible for measurements performed with instruments that are built in machine shops that are themselves built using Euclidean geometry. It is logically impossible for measurements performed with such instruments ever to refute Euclidean geometry. It was just the craziest version of a Neo-Kantian reaction. Einstein paid attention to all of this stuff. He was intensely interested in these debates with the Neo-Kantians. So already July of 1918, he writes to Max Born. I'm reading Kant's Prolegomena here, among other things, and beginning to comprehend the enormous suggestive power that emanated from the fellow and still does. Once you concede to him merely the existence of synthetic a priori judgments, you're trapped. I have to water down the a priori, and now this is important, I have to water down the a priori to conventional, so as not to have to contradict him. But even then the details do not fit. Anyway, it is very nice to read, even if it is not as good as his predecessor Hume's work. Hume also had a far sounder insight. Or here he is writing to Ilse Schneider, who was herself writing a dissertation on, she was a student of Alois Riels, the Neo-Kantian philosopher at the University of Berlin. She was herself writing a dissertation on general relativity and spent a lot of time meeting with Einstein and discussing things with him. Here's Einstein to Ilse Schneider, 15 September 1919. I've received the mentioned dissertation by Ewald Salien, Epistemology and Relativity Theory. Kant's celebrated view on time reminds me of Anderson's tale about the emperor's new clothes, except that instead of the emperor's clothes, it concerns the form of intuition. There's another letter with a downright vulgar comment he makes to her about Neo-Kantians, but I'll spare you that. The best Neo-Kantian reaction, one of the two best, came from Ernst Cassirer in his 1921 book on Einstein's theory of relativity. And very quickly, Cassirer's approach is to argue that Kant's mistake was arguing for the a priori status of a specific metrical structure. Cassirer said the lesson of general relativity is that what's a priori is a topological structure and not a metrical structure. So you want to weaken the a priori. Einstein interacted regularly with Cassirer, and he wrote this to him on 5 June 1920. I can understand your idealistic way of thinking about space and time, and I even believe that one can thus achieve a consistent point of view. To me, as a non-philosopher, philosophical contrarieties appear more contrarieties of emphasis than of a principled kind. What Mach calls connections are for you ideal names, which experience first makes possible. But you emphasize this side of knowledge, whereas Mach wants to make them appear as insignificant as possible. I acknowledge that one must approach the experiences with some sort of conceptual functions in order for science to be possible. But I do not believe that we are placed under any constraint in the choice of these functions by virtue of the nature of our intellect. Conceptual systems appear empty to me if the manner in which they are to be referred to experience is not established. This appears most essential to me, even if, to our advantage, we often isolate in thought the purely conceptual relations in order to permit the logically secure connections to emerge more purely. So he dissents from Cassirer's way of responding to GR. And now to the crucial moment, sort of the turning point in this whole story, which is occasioned by the publication in 1920 of Hans Reichenbach's first book, Relativity Theory and A Priori Knowledge. The central thesis of this book is yet a different way of, a different kind of Neo-Kantian response to GR. And bear in mind, Reichenbach is a Neo-Kantian at this point. He hasn't yet become part of the logical empiricist camp. His way of doing this is to say, well, we have to disentangle two elements of the a priori. We must disentangle the constitutive or constructive role of the a priori from the apodictic or necessary character of the a priori. And then having done that, we have to concede that one of the lessons of general relativity is that we have to let go of the claimed necessity of the a priori, but still hold on to the Kantian assertion that there must nonetheless be an essential constitutive, constructive function in the way scientific cognition works. And specifically in the form of what he called contingent a priori constitutive principles of coordination that make possible the ascription of empirical content to physical theories. Everybody read this book, argued about this book. There was at least a three-way correspondence involving Einstein, Schlick, and Reichenbach. Schlick wrote to Einstein, 9 October 1920. In the last few days, I have read with the greatest pleasure the booklet by Reichenbach on relativity theory and a priori knowledge. The work really appears to me to be quite splendid, a quite splendid contribution to the axiomatics of the theory and of physical knowledge in general. Of course, in a few points, lost my track here. Of course, in a few points, I still cannot entirely support Reichenbach. Reichenbach seems to me not to be fair with regard to the theory of conventions of Poincaré. What he calls a priori principles of coordination, and rightly distinguishes from the empirical principles of connection, seem to me to be wholly identical with Poincaré's conventions, and to have no significance beyond that. His reliance upon Kant seems to me to be carefully considered, only purely terminological. And then he wrote to Reichenbach himself, 26 November, "For me, the presupposition of object-constituting principles is so self-evident that I have not pointed it out emphatically enough, above all in my general theory of knowledge." His big book in 1918. It is quite clear to me that a perception can become an observation or even a measurement only through certain principles being presumed, by means of which the observed or measurement object is then constructed. In this sense, the principles are to be called a priori. But they are indeed, moreover, indeed, moreover, two possibilities, that those principles are hypotheses or that they are mere conventions. In my opinion, precisely this turns out to be the case, and it is the central point of my letter, that I cannot discern wherein your a priori propositions are actually distinguished from conventions. Reichenbach writes back, "You ask me why I do not call my a priori principles conventions. I believe that we will easily come to agreement about this question, even though several systems of principles are possible. Nevertheless, only one group of principal systems is always possible, and precisely in this restriction there lies some knowledge. Every possible system signifies in its possibility a property of reality. I miss in Poincaré an emphasis on the fact that the arbitrariness of the principles is restricted in the way one combines principles. For that reason, I cannot adopt the name convention." And then Schlick writes back, "On the question of the conventions, if Poincaré did not explicitly emphasize that conventions are not independent of one another, but are always possible only as groups, still one would naturally do him quite an injustice if one believed that he was not aware of this circumstance." I won't read this whole quotation. What's happening here is that the whole community is ganging up on Reichenbach and saying, you know, this is a really beautiful work that you've come up with, but there's just this one fundamental mistake. You just want to cling to this notion of a priori, of the a priori, in this attenuated, eviscerated form of these contingent a priori coordinating principles. And they're all just saying to Reichenbach, why don't you just give up the Kantian part of this and admit that what's distinctive of those principles is, as Poincaré taught us, their conventional character, rather than the honorific of the a priori. In this essay, again, I'm going to read the quotation, 1921, called "Critical or Empirical Interpretation of the New Physics." In short, what Schlick argues here is that if we take that turn, if we follow that Poincaré path of seeing the coordinating principles as mere conventional coordinating definitions, then we construct what he calls a new kind of empiricism that will be a vast improvement on what he here terms the sensualism of Mach, and will also provide us with a powerful set of tools for opposing Neo-Kantian assaults on the general theory of relativity. Let's skip that slide too. Where this leads is that by 1924, when Reichenbach writes his next book on the axiomatics of the relativistic theory of space and time, we see here finally emerging that classic core right-wing logical empiricist philosophy of science that I alluded to way back at the beginning of the talk. He says here, for example, that it's characteristic of the axiomatization of physics compared to that of mathematics that there exists such a distinction between axioms and definitions. An essential task of the axiomatization consists in tracing this distinction within the theoretical system. However, even definitions in physics are different from definitions in mathematics. The mathematical definition is a conceptual definition, that is, it clarifies the meaning of a concept by means of other concepts. The physical definition takes the meaning of the concept for granted and coordinates it to a physical thing, that is, a coordinating definition. Physical definitions, therefore, consist in the coordination of a mathematical definition to a piece of reality. One might call them real definitions. Again, for the sake of time, I won't read this slide. This is just the 1928 book where he makes, again, essentially exactly the same point and emphasizes the conventional nature of those coordinating definitions. So now these two narrative lines are going to come together. And remember I talked about Carnap before. This is the moment where these two argument threads, the argument about univocalness, Eindeutigkeit, point coincidences, categoricity, so on and so forth, and the argument between the new empiricists, the right-wing logical empiricists, and the Neo-Kantians. This is where it all comes together, is at this moment in this remarkable essay of Carnap. And again, remember the way he distinguishes proper concepts as categorical, explicitly defined in terms of empirical primitives, from improper concepts, higher theoretical concepts that are implicitly defined by their role in the axiom system. And then he says this: if the systematic construction of the knowledge of reality, or in the systematic conception of the knowledge of reality, real concepts are constituted step by step. As a term in this construction, every real concept poses an immediate relation to reality. By contrast, improper concepts, so to say, hover in midair. They are introduced through an axiom system that does not refer directly to reality. The axioms of this axiom system and the theorems deduced from them do not properly constitute a theory, since indeed they deal with nothing determinate, but only a theory schema, an open form for possible theories. But if, in the system of knowledge, a real concept appears for which it can be shown empirically that it has the formal makeup indicated in the axiom system for the improper concept, then the axiom system has found a realization. In place of the improper concept, which is just a variable, the real concept can be substituted. Thus, the structures of physical space, points, lines, etc., evince empirically the makeup that the axioms of geometry express for points in the improper sense. Through this contact between the real concept, the proper concept, the categorical concept, and the axioms, the former satisfy the latter. The connection to the entire theory schema based on the axiom system is accomplished in one stroke. And then I love this line. The blood of empirical reality streams in through this one point of contact and flows into the most highly branched veins of the heretofore empty system, which is therefore transformed into a filled out theory. And I'll skip a couple of things for sake of time and go back to Einstein himself, who had been thinking about these questions for more than 15 years by this point. I'll skip this, couple of comments from his 21 essay, Geometry and Reality, and jump to two letters that really give us a sense of Einstein's thinking at this time. This is a letter to a philosopher named Eberhard Schimmer, 27 September 1922. That which you work out in your essay seems correct to me, at least from the physical side, which is all that I can judge with certainty. In my own opinion, though, the important question to the opposition of relativity theory and Kantian philosophy does not emerge sharply enough. Are the spatio-temporal, etc. forms, which also ground a priori the relativity theory, only convenient tools of descriptions to be appraised as conventions, or are they givens, necessitated simply by the character of human thought, and inalterable in detail? I myself occupy the former standpoint, the conventional standpoint, represented also, for example, by Humboldt and Poincaré, whereas it appears to me that Kant's standpoint was more the latter. Even more revealing of Einstein's way of thinking is, well, let me skip this slide, is this review that he wrote in 1924 of yet another one of these books by Neo-Kantians thinking about general relativity, a man named Alfred Elsbach, where Einstein writes this: "This does not, at first, preclude one's holding at least to the Kantian problematic, as, for example, Cassiro has done. I am even of the opinion that this standpoint can be rigorously refuted by no development of natural science, for one will always be able to say that critical philosophers have until now erred in the establishment of the a priori elements, and one will always be able to establish a system of a priori elements that does not contradict a given physical system." Let me briefly indicate why I do not find this standpoint natural. A physical theory consists of the parts, elements, he doesn't mean that in Mach's sense here, A, B, C, D, that together constitute a logical whole which correctly connects the pertinent experiments, sense experiences. Then it tends to be the case that the aggregate of fewer than all four elements, for example A, B, D without C, no longer says anything about these experiences, and just as well A, B, C without D. One is then free to regard the aggregate of three of these elements, for example A, B, C, as a priori, and only D is empirically conditioned. But what remains unsatisfactory in this is always the arbitrariness in the choice of those elements that one designates as a priori, entirely apart from the fact that the theory could one day be replaced by another that replaces certain of these elements, or all four, by others. In effect, what Einstein is doing here is he's deploying this kind of Duhemian holist way of thinking about the structure of scientific theory, now as an argument against Kant. The problem is you can slice and dice the web any way you want and arbitrarily designate this the a priori component and this the empirical component, but as it says, what's objectionable is that it is entirely arbitrary from a logical point of view how you do this. I'm going to skip a little bit more here. And let's get to the end. Einstein the contrary. By the late 1920s, Einstein, who had once been a very good friend of Schlick's, began to cool rapidly because he was profoundly unhappy with the direction in which logical empiricist, especially right-wing logical empiricist, philosophy of science was headed. He said in an amazing letter, 28 November 1930, to Schlick, his once very close intellectual friend, generally speaking, your presentation is commenting on an essay of Schlick's. Your presentation does not correspond to my way of viewing things, inasmuch as I find your whole conception, so to speak, too positivistic. Indeed, physics supplies relations between sense experiences, but only indirectly. For me, its essence is by no means exhaustively characterized by this assertion. I put it to you bluntly. Physics is an attempt to construct conceptually a model of the real world, as well as of its law-governed structure. To be sure, it must represent exactly the empirical relations between those sense experiences accessible to us, but only thus is it chained to the latter. You will be surprised by Einstein the metaphysician, but in this sense, every four- and two-legged animal is de facto a metaphysician. And then, lastly, there's an amazing exchange between Reichenbach and Einstein in the Einstein-Schulp volume, Albert Einstein, philosopher, physicist. Reichenbach had contributed this essay, The Philosophical Significance of the Theory of Relativity, in which he had written the following. Another confusion must be ascribed to the theory of conventionalism, which goes back to Poincaré. According to this theory, geometry is a matter of convention, and no empirical meaning can be assigned to a statement about the geometry of physical space. Now, it is true that physical space can be described by both a Euclidean and a non-Euclidean geometry, but it is an erroneous interpretation of this relativity of geometry to call a statement about the geometrical structure of physical space meaningless. Choice of a geometry is arbitrary only so long as no definition of congruence is specified. We need a coordinating definition. Once this definition is set up, it becomes an empirical question which geometry holds for a physical space. The combination of a statement about a geometry with a statement of the coordinated definition of congruence employed is subject to empirical test and thus expresses a property of the physical world. The conventionalist, by which he means the purely geometrical conventionalist, overlooks the fact that only the incomplete statement of a geometry in which a reference to the definition of congruence is omitted is arbitrary. If the statement is made complete by the addition of a reference to the definition of congruence, it becomes empirically verifiable and thus has physical content. Einstein replied to this passage in his replies to critics at the end of the volume with this amazing argument. Non-positivists, that's an allusion to a wacky part of the Reichenbach article, needn't occurs. So this is Einstein speaking to Reichenbach. If, under the stated circumstances, you hold distance to be a legitimate concept, think metric interval, something like that, how then is it with your basic principle that meaning equals verifiability? Must you not come to the point where you deny the meaning of geometrical statements and concede meaning only to the completely developed theory of relativity, which still does not exist at all as a finished product? Must you not grant that no meaning whatsoever in your sense belongs to the individual concepts and statements of a physical theory, such meaning belonging instead only to the whole system insofar as it makes intelligible what is given in experience? Why do the individual concepts that occur in a theory require any separate justification, after all, if they are indispensable only within the framework of the logical structure of the theory, and if it is the theory as a whole that stands the test? This is pure Pierre Duhem from Einstein here. And the date is remarkable, 1949. He wrote the replies in 1948, because this is shortly before Quine publishes Two Dogmas of Empiricism. I took this paragraph many years ago, and I wrote to Quine, and I quoted it to him, and I just said, any chance that, before you wrote Two Dogmas, maybe you had read this passage from Einstein? And Quine, of course, wrote back and said, oh, no, I've never seen it. It really is quite long. One final point, and we will stop. Well, almost final point. This can seem like it's a purely philosophical dispute that's going on here about how we understand the logical structure and the empirical interpretation of scientific theories. Do we understand it in the right-wing logical empiricist way? Do we understand it in the holist, Duhemian, Einsteinian, Quinean way? But it actually makes a difference in how we do our physics. And a clear illustration of this comes from Einstein himself. And let's go all the way back to the winter semester of 1910-1911. And Einstein's lecture notes for the course he was teaching on electricity and magnetism at the time. He's at a point in the course where he's pondering the concept of the electron. And he's wondering out loud in front of his students, for the sake of his students, about whether the concept of the electron is even a meaningful concept. And by electron here, we mean, for the sake of this discussion, a solid body with a continuous charge distribution throughout the body. And the problem that Einstein raises is, he says, well, if you're a Machian, and if you think every individual element of theory has to be independently verifiable and testable, how would that work in the case of this model of the electron? How do we test the intensity of the electric field? Well, what we do is we take a test charge and we bring it near and we study the reaction of the test charge. But of course, you can't do that in the interior of a solid charged sphere. So wouldn't it seem to be the case that that's an impossible model if you think like a Machian, if you think that each individual element of the model has to be independently testable. Happily, there are other ways to think. He writes, "We have seen how experience led to the introduction of the concept of electrical charge. It was defined with the help of forces that electrified bodies exert on each other. But now we extend the application of the concept to cases in which the definition finds no direct application, as soon as we conceive electrical forces as forces that are exerted on material particles, but on electricity. We establish a conceptual system." Here comes the kicker. "We establish a conceptual system whose individual parts do not correspond immediately to experiential facts. Only a certain totality of theoretical materials corresponds again to a certain totality of experimental facts. We find that such an electrical continuum is always applicable only for representing relations inside of ponderable bodies. Here again, we define the vector of the electrical field strength as the vector of the mechanical force that is exerted on a unit of positive electric charge inside the ponderable body. But the force thus defined is no longer immediately accessible to experiment. It is, however, a part of a theoretical construction that is true or false, i.e. corresponding or not corresponding to experience, only as a whole." So here's invoking Duhamian holist underdeterminationist conventionalism to legitimate that way of modeling the structure of the electron. So that philosophical debate is making a crucial difference in that one little bit of Einstein's physics. Almost the last slide. The last slide is an absolutely shameless advertisement, totally shameless advertisement. And that is, go out and buy my lectures for the great courses. Philosophy, humanitarian. Teach you everything you ever wanted to know about. I'm done. Thank you, guys.
Time for questions?
Yeah, we've got 10 minutes of questions.
So yeah, I mean that was all fascinating. I'm just curious about the sense in which Einstein is approaching Quinian holism rather than some sort of less global holism. I mean, because it seemed like the sort of phrasing he was using there was to do with theories as the unit of empirical significance rather than the whole of science. So I was wondering, I mean, is there a sense maybe in which Einstein is more sort of objecting to the division of labour between the sort of abstract schema that then is imbued with the blood of empirical experience, or whatever that phrase was.
Yeah.
I mean, and maybe he's more objecting to the need for some sort of coordinating language for expressing experience, and maybe it's more about just taking the theory as a whole, and then whatever coordination with experience is to be found in theoretical terms. Would that be a...
Well, that's a minimalist reading of his version of holism. And to be perfectly honest, the evidentiary record is too thin to settle the question how far down the Quinian path he would go. You know, would he say that underdetermination still obtains in the face of the infinity of all possible evidence? I mean, there's no text I've seen that would help illuminate that. But that, it's a view that extends beyond just the understanding of scientific theory narrowly considered, is suggested by that letter I shared with you where he said to Schlick, if two different peoples did physics independently of one another, they'd start with the same set of impressions, but they could erect these constructs on that basis that can be radically different from one another. There's nothing about the view that he's giving there that confines that point just to scientific representations of reality in some narrower sense. Another way Quine is a radical Duhamian holist underdeterminationist is it is talking about how the underdetermination goes all the way down to the level of the observation sentences. And there is interesting evidence on that point. There is an exchange of letters with his old Olympia Academy friend Sullivan in the 40s, where he tries in great detail to lay out what exactly is his view of the structure and empirical interpretation of theory. And when it gets to the point where you've got your empirical basis and then you've got the world out here, up above that you've got these sharp, clearly demarcated lines that indicate definitions and constructions and something. When it gets to that point, instead of having these sharp, clear lines, what he has is these little dashed lines from the empirical basis down to the world. And he says in the letter, well, the reason I represented that as these dashed lines is he says, because at this point that connection is, now the word is not as helpful as it could have been, but the word, he says, it's just an intuitive connection. And that to me suggests that he also understood that Quinian point, that even down at that base level, there's an important element of underdetermination in the choice of those base level empirical concepts. But it's a perfectly good question, and I don't want to push too far. A critic of mine, one paper I wrote a number of years ago, accused me amusingly of having invented a fictional character that he called Albert Van Orman Einstein. And I pled guilty as charged on that occasion.
So at least Carnap's sort of resistance towards this holism was in particular in relation to constructed languages. So a lot of his dispute with Quine was over sort of what central role should natural languages play in this story, and Quine's holism was of particular significance in relation to natural languages. So I'm just wondering how Einstein is placed in this sort of discussion between natural languages and constructed languages, because general relativity is a constructed system. So I guess someone like Carnap would precisely say we have partial interpretation of the theoretical terms, and then this is via the protocol sentences. And wouldn't Einstein agree with that to quite a degree?
Well, here's another place where the evidentiary record is too thin to allow us to say anything really firm about. He doesn't display much of an interest when these discussions move in a more narrowly philosophy of language direction. So I don't know that I've ever seen him pondering in a careful way the distinction between natural languages and formalized languages. So again, it's hard to say. As for what his attitude toward Carnap specifically was, whether on this specific point more generally, there is, however, a very amusing piece of evidence. In the early 50s, when Schlick was putting together the Carnap volume of the Library of Living Philosophers, knowing that Einstein had been a colleague and correspondent of Carnap's for many, many years, he had solicited an article from Einstein. And Einstein wrote back to Schlick this wonderfully amusing letter where he says, among other things, he says, that when he was young, he was more enthusiastic about logical positivism, and then he says, in its youth, it was this fresh and frisky young colt, but now it has just become this this staggering old nag, and it's sort of lost its purpose and its way. And at another point in the letter, he complains about the insistent nattering of these, he calls them positivistische Vögelchen, which is hard to translate into idiomatic English, but it means like positivistic little birdies, right? And there's the constant nattering of them. And it's clear from that letter that while there was a lot that he admired about Carnap the person, that he, certainly by that point in his life, he was just totally sick and tired of Carnap's philosophical project.
Yeah, so it's maybe saying that the displaying, at least Carnap, but I think to some degree other Utopian right-wing logical positivists.
And actually, one has to be careful on that.
Yeah.
Placing of Carnap on the spectrum of opinion. In his case, it's a little bit more complicated than it is with Schlick and Reichenbach.
Well, I will leave it. We can discuss it later.
Yeah.
I have a question from, I'm a physicist, not a philosopher, so I'm interested, I found your discussion very interesting about Einstein and his discovery. But for me there's a form of, and I want to know how you react, a form of ambiguity in his position. He said, between Einstein the philosopher and Einstein the discoverer. That is, I was a bit surprised by one of the letters you showed at the end about when he presented this holistic point of view about the electron, that he emphasized that it's important to have elements of the theoretical system that might not be individually testable. Because when you read Einstein, his papers, his discovery paper, he's very close in philosophy to, I would say, Heisenberg, which is that he focuses on always insisting that the theory should be formulated in terms of the fundamental observables, like what you call the coincidence of points. So there's kind of a...
So which, are you talking about the 1905 paper?
Yeah, or more generally, in fact, most of his papers are have this quality, that which is the quality of Heisenberg's paper, that they say, well, I don't want to talk about things that do not exist, that are not embedded in the real world. I want to draw relationships between things that exist, and somehow this focus, this is what they give them this edge, and you can see how important it is in the discovery of the physical theory they had. So somehow Einstein, the discoverer, has this very sharp focus that there are things that are irrelevant in the construction of physical theory, maybe kind of necessary as stopgap measures, but later he seems to, I don't know, emphasize them. So you see, I'm like there's a shift.
There is a shift.
Is it?
There is a
which
shift.
I find a bit. Okay.
So in his early years, he was more strongly enamored of Mach's version of positivism, and you see much of that in the 1905 special relativity paper. But by the time you get to 1915, that has receded well into the background, and by the early 1920s, there's an abundance of letters and other sources where he's hugely critical of that sort of naive Machian point of view. And he evolves in the direction of a more robust realist over those years. So in those discussions about the point coincidence argument, it's fascinating that he so tightly linked the question of the observable with the question of the real. A Machian would have just foregrounded questions about observables, but for Einstein, the two seem to be incapable of being disentangled from
So, but from that point of view, the point coincidence is very important. It's something which is real, right? So
both real and observable.
Yeah, both real and
observable.
Both
by virtue of the invariance
yes,
of those.
Yes. So the tension is later, he seems to advocate, or that's maybe misunderstood, the importance of introducing objects that are not real in the theories, like when it's, discoordinatization. So the point coincidence is the real element of geometry. But of course, when you theorize it, you have to introduce coordinates or things which are not real, which are so there seems to me, I don't know, maybe I misunderstood, there seems to be a shift between emphasizing that what's only real is the point coincidence, and it's important to have elements which are not real in the theory.
Well, give me an example of what you take to be an element that's not real. in the theory.
Coordinate systems.
Well, so in that case, he's very definitely saying that's just not real. And
Yes.
it has to be there in order for us to have a language in which to talk about our measurements and so forth.
Yeah.
But he was, of course, quite adamant that it's not to be understood as having any ontological significance whatsoever. So it's not like some theoretical posit, the ontic status of which is up in the air. No, it's just something that you have to use, but has no ontological significance whatsoever.
But you seem to imply the end of this believing that this has to be a necessary element of the theory. That the theory necessarily has to contain these redundancies. These redundancies, these objects which are not real.
I think we're using the notion of real maybe in a couple of different...
No, I mean, it's coordinates.
But I mean, if the point is just that, yes, I mean, it's redundant and arbitrary and so forth, yes.
Hey, please, should we make that like an hour and a half, I think? Should we retire to the pub for questions?
I can ask you that.
Thank you, Dom.
Yes, let's continue discussion in the pub. Always a good place. The university.
I don't like drinking. But the pub